Gene is the president and CEO of MANEX Consulting. He has over 30 years of experience in the manufacturing sector, including 2 previous CEO engagements in both the private and publicly held companies. Mr. Russell's current mission within MANEX and with the MEP program is California's manufacturers and helping the small and medium-sized businesses specifically. It's critical that we engage, assist, and develop California's manufacturing sector. And according to the National Association of Manufacturers, manufacturing in California account for over 11% of the total output of the state and employ 9% of the workforce. So we'll hear more about that. I'll turn it over to you, Gene.
Thank you. Thank you, Rob.
You betcha.
Good morning. Yeah, we have a really interesting panel here, and it strikes me, having spent some time in telecom and IT over the last 30 years, that we're at a really interesting tipping point in manufacturing that reminds me of some of the transitions that went on in telecommunications and in IT, and additive manufacturing is certainly one of those areas. And the panel that we have here today, Rich Chen, Gonzalo Martinez, and Patrick Dunne, can give us sort of a view to that. Gonzalo Martinez is Director of Strategic Research within the CTO office at Autodesk, which is the large software provider that everyone's familiar with in 3D printing. He has a engineering manufacturing degree from Boston University. Also Rich Chen, VP of Design Engineering with Microfabrica, which operates within the micro machines world, which is quite exciting, and he'll be speaking to that. And also Patrick, Director of Applications Development at 3D Systems, which is the hardware printer world, where they've developed some exciting printers at various price points, including in the consumer area. So I'm not sure how we're going to stage the presentations, because some of them are using their laptops for security reasons, just as we did before. So maybe, Gonzalo, would you like to start?
Just give me a second, I need to plug my system here.
Need sound too.
No.
Okay, good morning, everybody. So my name is Gonzalo Martinez. I work for Autodesk, and I have the privilege to come today with the Sonoma County BEST team to the facilities here. So how many know about Autodesk? How many of you guys use Autodesk products? Okay, so a lot of customers, so it's very, very good. I'm not gonna, oops, what's happening here? I'm not going to talk about, we have a very vast product portfolio at Autodesk. How many of you guys are using AutoCAD, still using AutoCAD? And we have so many other products besides AutoCAD today. But what I want to talk to you today is about technology. 4 trends that we are looking at Autodesk are very, very interesting. All us remember this old phone and how far we have moved through from there to here. Our old TV, I never had one like this one. Mine started with a little bit of color. But how kids right now, I mean, my sons all day are looking at YouTube. They're training themselves. In fact, they say, the other day, Dad, we don't need to ask you a question. I said, why? Because we Google everything. So we at Autodesk, when we develop software, we're looking, what our customers are looking, what is expected, what is required. But sometimes you need to be looking at, what is the curve between possibility and expected, and sometimes you still have to be looking at the impractical in terms of, getting to the next level of technology. So one of the technology trends that we started out of this is what we call reality capture. Is, how we bring the physical world into the digital. Because we have so amazing tools to deal with the digital world, but we need to bring it to the physical, from the physical to the digital. So this is the case, of this maze of freeways. And some of our customers, they need to add changes to that freeway. And as soon as they go into their software from what they have right now, that's all they have, a blank screen. So how I bring all this stuff into this blank screen, from physical to digital. And, there's the proliferation of new devices, that allow us to scan, from $35,000, you can capture a tremendous amount of data to systems that are more affordable today. And for instance, this is a geometry that we capture with a laser scanner, typical point cloud data, but now we render with color. And you can see, very, very clear, this is coming directly from the scan data. And I'm going through a tremendous amount of gigabytes of information right now. I'm flying through, I'm able to analyze and capture that. So that brings us the means to create tools to move some of this data around and how we're going to be working with this data. There's devices like the Kinect today, and we are developing software about how to capture geometry and shapes and forms. This is interesting. This is a test that we did in the in a mobile device, and most of you will think this is a photograph. Actually, no. This was a point cloud data that we were able to generate from the phone, completely three-dimensional. This is another one that I captured with my iPhone. I was around the Notre Dame and captured different angles, the pictures of the church here, and be able to render it automatically and have that kind of information. So for us, and that's what we call it reality capture. To bring from physical to digital is very, very important for us. We start seeing these devices because what about we want to go airborne, we wanted to make airborne very, very affordable. And in fact, we built, some what we call UAS, drone systems. I took one of these drone systems to Africa, and we were flying over archaeological sites and taking high-definition video and imagery and generating, some topography from there, which was fascinating. You can see a clash of cultures, me using a traditional hat, and then we have this chief, which was a very nice guy, but he carried an AK-47 24 hours. So I was a little careful about that. And it was fascinating because every tribe that we went there, we had to ask permission to fly this strange thing. So this was one of the octos that we built. We fly manually. We open a Google map. We set up points, send it on a mission to do the mission. Or one of my favorite flights, what we call FPV, through these goggles that have full telemetry. I go to a distance of 1,000 meters. And I can capture and activate the octo to do whatever we want. This is a flight path that I designed in front of our main building in Marin County. And it was interesting, from photograph, I was able to generate this geometry completely three-dimensional. And just from the images, I don't have to even tell the system where's the image. I just give it an array of images. In this case, we're 150. And I say, from this array of images, you compute me the three-dimensional of this building itself. But it goes beyond that. What we do with this data, how we analyze this data, how we simulate, the lighting, the air distribution. And if you don't have the model, there's tools right now that allow you to capture the model and bring it three-dimensional. Probably all of you know this famous actor, how we scan him, and for the movie Tron, we make it younger. And all these tools that are available to do from the software side. So democratization of this device is very important for us because it will allow so many people to do things that they never thought they could do before. Cloud data, very important for us. So we did a reality capture, cloud data. Now we have to deal with massive amount of data. And we are building the systems of the future to allow us to have this data, to access this data, even from a mobile device, and do things with that data itself. From the building information model, how I'm going to be using this survey data, and how all this data communicate to each other to either simulate, fabricate, manage, and how all this data is working. I mean, if you look at this maze of pipes, I mean, be able to go at any point in any place and extract the information is quite important. This is a simulation of this city that you can see here, completely digital, but the interesting part is right now, I can go into any of those buildings and go to any floor and ask blueprints for that, and I will have the information almost instantly. So the other thing is, now that we manage this tremendous amount of data, the infinite computing, how can we use the power of the system? So you can see this farm of servers here doing some amazing stuff. We calculated a customer will typically use one processor. It will take 10,000 seconds and it costs 25 cents, okay? Well, it's interesting how it scales because we did the same thing. We used 10,000 processors, and in 1 second, it was the same cost. So nowadays, a lot of the software that you're using from Autodesk, it will do this heavy computing on the cloud, and it will bring instant results, not only of the thing that you were looking, but also with alternatives. Instead of spending so much time having the system be able to tell you some alternative. And this is the case of computational evolution that we do. Now, simulation, extremely important for us. How we simulate sound, how we simulate heat, lighting into a building, and the tools that we are developing to do that. This is a case of a simulation to how people will leave this building in case of an emergency, and be able for you guys to calculate all these elements. This is interesting. This is a full simulation. One of these pictures is real, and the other one is fully rendered. How many will you say this is real? Okay. How many will say this is rendered? Okay. Let me look at again. Okay. So this one is real, and this is rendered. Okay. Now let's test you again. How many of you will say these are real? You guys are wrong. All of them, they are simulated. This girl only exists in the computer, okay? And we was generated with our software. So many advances in terms of that. This was an operation room, and they have a problem with organisms flying in this operation room. And it was all done because of the bad design on the venting system. So we went there, we look at this whole thing, we look exactly at the flaws that were happening, and we redesigned with them to get this kind of output. All these tools. So that's why it's so important, bringing from physical to digital, because in the digital world, you can do so much. This is another simulation. It terrifies me every time that I see this simulation because I work in One Market Street in San Francisco, and just to see, how the simulation of this software right now, it will simulate, an earthquake, and things start collapsing and breaking in pieces. It scares the heck out of me. Yeah, this is the last part that is pretty bad. So simulation is very key, because before you guys build this element, you need to simulate. Now, one of my favorite topics, which is digital to analog. You say we talk about from physical to digital, now back from the digital to the physical, by different means of additive manufacturing, subtractive manufacturing, robotic, nanoscale, and bio, and we are out of this, we're looking at every single level. Okay, we are making, a lot of progress in our software to address all these technologies. It's interesting because, we talk about so much about 3D printing, and by the way, we love 3D printing, but it's another method. It's another method that will coexist with many other methods today. So some of the materials that you guys can do in 3D printing, the famous word from Star Wars, the replicator, Star Trek, I'm sorry, from the replicator stuff. This was a Nike shoe, fully 3D print. Okay. Probably you guys have seen some of the fashions, about being able to 3D print as well. This is something that we did metal sintering, and it came out really nice. This actually is a design that our CEO did it himself. And to go into larger scale as well. If you want to start printing, at the building level, or even at the nanobiology level too as well. We are looking at all these technologies as it is. This is something that I did with the Main Space Group. Actually, I was the one who took the picture here. We went in the zero-G flight with NASA, and we were testing 3D printing at zero gravity. And the reason is because we're going to put a 3D printer in the space station. Remember that movie, Apollo 13, Houston, we have a problem? When it should be, Houston, we have a problem, send us the design because we're going to 3D print it here. Okay, so that's very interesting stuff that we have been looking at the technology. By the way, it was fascinating. It was absolutely fascinating. This is called a vomit comet, and I didn't vomit, which was great. But it was really interesting. Actually, we print a wrench, and we were able to do it. Things, were, medical, and technology-based. This is an implant that it was a man that had this terrible accident in India and lost this bone structure here, and from MRI we're able to produce the other side, massage a little bit the other side, 3D printing in titanium, adding porosity to the metal so the bone will adhere and do that. I start printing my china. I'm not going to put anything hot there. Different elements that we did at Autodesk, a lot of the samples that you see in 3D printing, I'm going to make some here very fast, illustrates. A lot of them, they are small objects, that have function. Very complex to manufacture these kind of things. So we decided to do something a little bit bigger as a test. So we have this design of a motorcycle, fully 3D print, and we did a full-size 3D print. The interesting part is that we were able to simulate so well every piece that it was incredible. We have zero error when we printed. I had 2 months to finish this motorcycle. It was done in 5 weeks. So we did the motorcycle as a first test of something a little bit bigger than that. Then the following year, they asked me, can you do something bigger? And then we got this design, and we 3D print pretty much a full-size turboprop jet engine. And we have all the planetary gears connected with the electric motor, and we turn the electric motor, and you can see the props working and acting like they're supposed to be. We did process, of working with Jay Leno, of some very old parts of his cars that obviously he couldn't find it anymore. We went out there, scanned the part, get the shape of the part, remove the rust of the part, and generate a three-dimensional model of the part and 3D print the part that work. So all these technologies are quite remarkable. We are working stuff like, for example, I'm going to be able to have my iPhone here, and all of a sudden, I can see, through the camera, what's here in the walls itself. But if I look here and I say I want to see what is under the wall, it will allow me to get the blueprints underneath here and project it to me here on that position that I am. So this is what you see right now. You can see, what you see right now in this building and kind of the pipe system that they have there, which is really fascinating. And how you converge all these data together is very important. So reality capture, cloud data, infinite computing, simulation, digital to analog fabrications are things that we're looking, and how all these technologies connect together. In fact, for us, on the technology, we're looking at disruption, how to create some of the disruption there. Scale, from nano to global is very important, how we address those things. Data, discipline, building information model is very important for us. And the most important is to democratize, how to make these technologies available and very inexpensive to use. And sometimes you need to be looking at the impractical to get some great benefit from there. So that's pretty much for myself. I hope I did less than 10 minutes. At the end, if you guys want to see some of these very advanced stuff that we did with 3D printing, this was 3D printed with the strategy system. Really flexible, multi-materials in one shot. So it's our intent to start developing software for engineers and consumers, how to use these multiple materials, because it's going to change the way we manufacture things in the future.
That was fantastic. As you can tell, Gonzalo's been involved in this business for a long time. In fact, he was with Autodesk since 1991, right? Correct? Yeah, so a long time. Excellent information, and I think the disruptive nature of this technology speaks well to the tipping point that we're at. I would just add that you need to turn your iPhone into security before you leave. Oh, you did? Okay. So next, I'd like to invite Rich Chen up from Microfabrica, and he'll be giving his presentation. Thank you.
I am very excited to be presenting with some of these guys. A little intimidated and also honored. 3D Systems, Autodesk. I wish I used a little bit more multimedia in my presentation, but I have one video. So what I want to do today, I'm going to show you a little bit of what we do. I'll give you a brief background of Microfabrica. I'll show a video of our technology, and then go through just a few applications to give you a feel of what we can do. So to start off with, Microfabrica, we are a technology company, advanced technology company that has a proprietary micro-manufacturing process, and we could create very small micro metal parts very robustly and on the sub-millimeter to millimeter scale. So I think relative to a lot of other companies that you'll hear about today, we're a little bit different. You can't really see our parts. We're probably more similar to what Chris presented earlier from Lawrence Livermore. And we don't really print the parts, we electroplate the parts. We grow them additively through electroplating. So we provide manufacturing services that support product solutions in a couple different markets. One being the semiconductor market, the aerospace, defense, and finally the medical. And we really see the medical market being a very large market for micro mechanisms, micro devices. A little bit more about our history. We were founded in 1999, and we spun off of USC in 2001. We have a 40,000 square foot facility in Van Nuys, Southern California, and our founder and president both were actually from 3D Systems, so that might explain why we have some of our roots in additive manufacturing. Okay, so the process that we have is called microfreeform. Let me. And it's a little bit different than 3D printing. So first, how is it the same? We could build 3D objects with layers from a digital model. So we receive a digital model, and we could grow this three-dimensional shape. This allows for complex shapes and also eliminates assembly. And these are some of the aspects that we've been hearing all day about. What are some advantages of additive manufacturing? That's how we're very similar. But we're also slightly different than your typical 3D printing. We do parts in high volume. Because we make micro parts, we make parts in batch, in hundreds, thousands, 10,000s parts at a time. We hold precisions down to plus minus 1 to 2 microns. Again, most of our so-called competition is really standard conventional machining, and holding those tolerances can be pretty difficult. And we also use engineering grade materials, very high yield strength materials, which lead to robust micro devices. What you see on the right, this is a micro pair. This is a biopsy forceps. It's about 1 millimeter in diameter. It's all fabricated one piece. This is an SEM image, and you could actually see the layers of how we built them up. So next, I want to show you a video. This is my only multimedia part of my presentation, which will give you an idea of how we build these parts up. And we build them on what we call a wafer. And we can build multiple parts, many parts, all in batch.
This extraordinary process begins with a 3D CAD model. Using proprietary software, the model is divided into layers, allowing photo masks to be generated to sub-micron accuracy, with hundreds to even thousands of devices fitting on a single ceramic wafer. A custom photolithography process defines a pattern where the first layer of structural metal is deposited at the atomic level through electrodeposition. The photoresist is then dissolved, and sacrificial metal is deposited over the structural material. The surface is then planarized to a consistent uniform thickness, within a tolerance of 2 microns. The process is repeated for each layer in the design until all the layers are completed. The sacrificial metal is then abstracted through a chemical etching process, simultaneously enabling movement of each mechanism while releasing the device from the wafer. High-performance micro machines.
If you have any questions about the actual process, I'd be happy to answer them either after the presentation or maybe during the break. But so now I want to go through just a few applications of some of the things that we are doing with our customers today. The first application, this is semiconductor. In the semiconductor industry, we're calling it wafer test probe. They're micro contacts, micro needles that touch down on IC chips, Intel chips, Samsung, your flash chips, and make electrical connection to test those parts while it's still in the wafer format. So we actually work with a local company here called Form Factor, and they're in this industry. So what are some of the challenges of this? The industry, with Moore's law, all the chips are getting smaller and smaller. So are the pads on those chips. So the pitch on those pads are getting smaller and smaller, and they need to touch down on all those pads to make electrical contact. So these needles are getting, in the same way, very, very small. Less than 80 microns in diameter going to probably less than 50 microns in diameter. And at that point, precision is really, really key. Every micron counts. So there's this move to smaller dimensions, but then there's also a need for higher power. So they want to have more conductivity, more current to go through these microneedles. In the same way, they still need high reliability. These little micro springs, they look like eyelashes, cycle over 1 million cycles. So our solution, we've been able to make this micro composite device. It looks like a simple little wire. But the features are plus or minus 1 to 2 microns, so they're very precise. But it also has a composite set of materials. So we use 3 materials to make this little micro spring. The first material is a nickel cobalt alloy, and this provides the strength. So this provides the outside shell, makes it very strong and mechanical. We also have embedded copper down the center. This is where we could put high current through it. And then at the tip, we plate this with a rhodium, a pure rhodium material, which is very high wear resistance and makes really good electrical contact. So on this scale, being able to incorporate these 3 materials is pretty unique to our process. Okay, so the second example, this is an aerospace and defense application. It's called a safety and arming device. This part goes inside a 40 millimeter grenade. So what you see on the bottom left, this is 40 millimeters. This is the size of a conventional safety and arming device. It's about that big. The grenades, probably about that size. And the goal was to reduce the size, reduce the volume by 400 times. You could pack more explosive in it, that you could put more intelligence in this part, but also improve the accuracy of when it times. So improve the timing mechanism of this part. And really, this is almost like a little watch. It's a little escapement mechanism, 7 moving parts. So what we've been able to do is take this 40 millimeter device, shrink it down to about 5 millimeters in length, and about 700 microns in height. And this, what you see on the right, this CAD model, this is what the part looks like. Multiple pieces, fabricated all at once, no assembly. And here's an image on the bottom right. So it's survived some of these firing conditions, 1,500 Gs. Timing, we've been able to get it down to plus or minus 5 milliseconds. And again, all these parts fabricated at once. For us, this is a really good application. And again, there's really no way to make this with any other conventional technology except for an additive manufacturing process. Now, the last thing I want to talk about, which really is is probably the biggest growing area we think in additive manufacturing, and it's in the medical industry. And this is one example of one of the things that we're making and working with a medical company on. And this is a micro tissue removal device. So what you see on the upper right, this tip is about 2 millimeters in diameter, and it fits on the end of a handpiece that looks like a pencil. So you can imagine on the end of this pencil has this micro debrider, micro tissue removal device. What are the challenges? We want to make this remove material at a very high rate. It's going to be front cutting, and this is if you're in the industry, most of these devices that remove material are side cutting. Rarely is there a device that actually cuts from the front. And then also reducing this tip size to 2 millimeters and potentially smaller. One of the applications, tumor resection in the neurovascular area in your brain, being able to selectively remove material without damaging material on the side. So what we've been able to do is take this concept, which was really born out of a paper shredder or a tire shredder. You take these macroscopic ideas, shrink them down, because previously you wouldn't be able to make something like that on that size. If you had that as a solution you brought to your manager and asked them, I'm going to make this complex device really small, they wouldn't really know how to do that. They'd probably think you're crazy. So, but we've decided, well, let's demonstrate that. So we've made this device very complex, multiple gears, multiple moving mechanisms. We've been able to fabricate this in one piece, and the amount of material it removes is quite astonishing. It's hard to imagine with just pictures. I wish I had a video of it, but it does take. It's hard to imagine how voracious this type of device is, and it really sucks up the tissue, but at the same time, it's very precise. So the blade mechanisms, everything fabricated once with one piece. So the last thing, I'm just going to conclude on this slide. Really, the macro, the trends that we're seeing, there really is this drive to miniaturization in a lot of different areas. As I mentioned, semiconductor to aerospace defense, and then what we think is really a big area is going to be medical. And conventional machining, traditional machining technologies, it's really running out of steam. And one of the models we like to bring up is it impossible to machine? If it's impossible to machine, you have to use an additive process to really build it up to achieve that type of complexity or that type of precision. And this is why the evolution to additive manufacturing, we think a lot of areas, a lot of industries in the microscopic world are starting to migrate toward. So that concludes my presentation, and thank you all.
Thank you very much. I thought that was very exciting. I'm reminded of a couple of things as Rich took us through that fantastic overview, and that is that manufacturing, as we all know, because we're all manufacturing people, drives 90% of private R&D dollars. So that's very important for the United States. And manufacturing, as we probably should know from the McKinsey report that came out in November, and I'd like for everybody to download that and read it, it's very fascinating, drives 70% of trade or export, so it's very important. Next speaker, Patrick from 3D Systems, is going to talk from the hardware side, and I imagine there's going to be some even more exciting stuff to look at. Thank you very much.
Good morning, everyone. Okay, good morning, everyone. Patrick Dunne. I've been with 3D Systems since 1999. Pretty much focused on development of advanced applications, specifically rapid direct manufacturing, mass custom manufacturing. Currently located in San Francisco, where we've put an office just out of market. We have a full lab there now with all the equipment, so anybody who wants to discuss some of the nuances of utilizing layer additive to make things, then feel free to schedule a visit. So what I wanted to do with these slides is start off by not just putting 3D Systems, given the context of where 3D Systems comes from, and how it meshes with making. How do you make something? If somebody comes to you and says, I want to make an object, but also to put California kind of in context with respect to, its role and the role it played in bringing layer additive technologies to the world between 1986 and 1989. So if you look at our species, we first started making objects around about 2.5 million years ago, based on flint tools that they find in regions of Africa, which indicate a subtractive form of manufacturing where people were chipping at stones, removing material to create an object. This stepped up a gear about 78,000 years ago when people started using fire to splinter and crack and change rocks. Ultimately, subtractive, CNC machining, drilling, carving, sanding, cutting, chopping, anything in a lathe, any process where you remove material to create an object is what we fundamentally call subtractive manufacturing. The second form is formative, again, our species about maybe 8,000 years ago, Mesopotamia, melted copper or bronze. There's some debate. And the oldest object ever found that's been cast is actually an ornament. It's like a little frog, which is quite interesting, not an axe head. And you kind of see a lot of frogs on Thingiverse and Maker and all this kind of stuff again. It's kind of cool to see that we're back to making little ornaments. Ultimately, that led to the Iron Age and all these different technologies for melting, forming, casting, taking clay and squeezing it, melting glass and pressing it into cavities to create objects, blow molding, rotational molding. Again, these are all tools in a toolbox. If you're tasked with making something, you look in your toolbox and you think, what's the most efficient, cost-effective way to solve the problem? And the third form of making was actually invented in California in 1986. So that's just to put it in context. And it was with the development of stereolithography by Chuck Hull, came from a UV photopolymer background. And that led to all these different ways of building objects by sticking layers or voxels together. Today you have many different versions, techniques, including selective laser sintering, fused deposition modeling, MEMS modulation of light using DLP or pass-through, electron beam melting to get very dense, fully dense properties, inkjet binding, thermophoto inkjet, a whole bunch of different ways. What I said to Scott Summit earlier, it would be interesting in millions of years if they dig in Valencia and they find like an ultraviolet laser or something, and it could be the first representation of additive manufacturing. So just a little bit of a focus on the technology. SLA was the first technology, and just because it's the first doesn't mean it's become obsolete. It's SLA and SLS, both vector-based additive technologies, are still the industrial workhorse of the layer additive manufacturing industry. If you go out there and evaluate companies that are producing 100,000 objects a day, and they do exist at this point. A lot of it's below the surface and confidential. But you'll find that they're the backbone, the workhorses of those companies, and the service bureau industry is the stereolithography system and the selective laser sintering system. Reasons for that is lowest cost of production. If you make a part hollow, the liquid stays in the vat. Other printing technologies fill that hollow void with support material, which is expensive. Compatibility with post-processing. You can take a tray off a machine, put it through a conveyor belt, through dishwashers. You don't need to have any labor scrubbing and cleaning parts. Extremely high definition, very high throughput. It's vector, but you're moving a vector at tens of meters per second. You're not mechanically moving it nor extruding it. Very broad range of materials, everything from ceramic-loaded resins to transparent resins to biocompatible resins. There is full SPC coming out of systems now so that people can integrate them into manufacturing. Very high quality surface, minimum finishing, and instant turnaround. It's a non-thermal, non-contact buoyant process. So a build finishes within a minute, you can be building another part. SLS is the melting of powdered materials. Whole range of materials ranging from nylons, different grades of nylons, glass fill nylons. Very good accuracy and definition, high system consistency. Tough mechanical properties, not just in X and Y, but in Z. I mean, it is lower in Z, but the mode of failure is a mode of failure that's representative of the mechanical properties of the thermoplastic. It's not a welding versus, it's not a melding versus welding failure. It's not delamination, layer delamination. Fractures occur across layer lines. 3D nesting, you can stack parts three-dimensionally. There's no support structures. Parts are floating in a bed of powder. So it's support-free manufacturing. And then industrial design grade aesthetics. If you look at any of the websites selling lampshades and jewelry and nervous system and MGX or whatever, everybody gravitates towards selective laser sintering because the layers are almost invisible and the mechanical properties are very consistent and the sidewall looks like the top surface, looks like the bottom surface. So again, just looking at materials, a whole range. I'm not going to go into the list, but everything from class 6 biocompatible materials for making hearing aids, drill guides for dental implant placement, plastic, thermoplastic replicators, ceramics, high temperatures, compatibility with RTV is very important for preventing inhibition of polyurethanes. And SLS, we have flame retardants, we have high impact strength composites, glass fibers, through elastomerics, not just, a lot of the elastomerics and the other systems are just low durometer, but they're gels. They're not really elastic. If you make a gasket and you squeeze it and you release the pressure, it remains compressed because it's a yielding gel. Biocompatible materials and other plastics. Some examples of mass custom manufacturing, which is very different from low volume manufacturing, is where you have gigabytes of data flowing in, kilograms of powder flowing in, and then you have units of product shipping. It's largely a logistics. It's largely logistics. I've always said it's 15% technology, 85% logistics, because anything breaks, it's like a car crash or pile up on a freeway. Some of the companies doing it now, 3M is manufacturing all its prosthodontic models. There's 300,000 people walking around right now with crowns manufactured on dental models made using stereolithography. Siemens hearing aids, all the hearing aid companies, about 96% of all hearing aids in the world, custom hearing aids, are manufactured using stereolithography. Somewhere we're seeing a lot of traction right now is patient-specific surgical instrumentation. So again, enabling surgeons to create the perfect cuts in bone in order to place an implant that's like a jigsaw puzzle piece. So the patient is open for a very short period of time. You get very rapid osseointegration and very short duration of physiotherapy because it's the mechanism, perfect implant is placed. Obviously, custom orthodontics. Again, some of these operations are making up to 75,000 custom one-offs per day in facilities that look more like factories as opposed to just labs with single little machines. So just a quick snapshot of an example of a mass custom manufacturing facility that's happening right now. It's not theoretical in the future. There's millions of product being produced using layer additive. Also very large systems. This is a single piece dashboard. If you go to any of the automotive shows, the cars that you see in Detroit or in Switzerland, it's always, these days they're all made using layer additive 3D printers because of the fact you can convert a CAD file into a physical object very, very quickly, very accurately. Quick casting patterns. Some folks mentioned that 3D doesn't do metals. We're the largest supplier of metal components from rapid prototyping workflows in the world. We don't believe in directly making metals. We believe in producing printers that produce wax, so we can give it to a casting or a foundry guy who can then come back to you with an alloy that in any metal you want that's certified and representative of what has always been in, for example, aerospace programs. We also build very large components on very large systems. while still preserving detail. You know, you see that dashboard, if you zoom in on it, it could be covered in little pins like this. The correlation, I've always said that the correlation between cost and complexity is very, very low with three-dimensional printing. That's one of the main advantages of it over subtractive, where you have to express every feature with a vector. Again, casting, aluminum, titanium, anybody who works in aerospace, automotive, where you need to either make a prototype metal component or low volume. You know, if you look at Formula One, motorsports, if you look at UCAV, it's low volumes of complex components with extremely high complexity. It's very hard to justify tooling. So you can build a pattern, give it to a foundry, and they'll cast it in any alloy from titanium to aluminum. Again, Scott showed a slide of ceramics from a stereolithography system. You know, feeding that wind tunnel, so you don't have to turn off the wind tunnel. You can actually build a product faster than you can think of ideas. So the bottleneck is no longer converting the idea into a physical object for feeding that wind tunnel. So you get better utilization out of your wind tunnel. Optical clear resins, you know, this is all from the same machine. So on a Monday you could do a casting pattern, on Tuesday you could do ceramic, Wednesday you could do an optically clear prototype for the headlamp of a concept car. On Thursday you could put in a tough functional plastic and create a replica of what your injection molding is going to look like. And on Friday you could make some hearing aids that are biocompatible for sustained skin contact. You can make drill guides that surgeons can use to drill into bone and accurately place implants in the perfect position, not hitting the nerve, pre-designed using CAT scan information or X-ray information. Again, that kind of shows the range of applications from a stereolithography system. It's like a Swiss Army knife. If you have one within your company, there's a whole range of different departments and projects and programs that you can address with the technology. Same with sintering. You know, this is UCAV, non-structural plastic component manufacturing. This is an ECS ducting. Again, this is a program that required 22 ducts a year. How can you justify rotational molding? Put the CAD file on the 3D printer, on-demand manufacturing. You know, a lot of groups within the Department of Defense doing that right now. True elastomerics like gaskets, seals, patient-specific instrumentation for drilling, cutting, removing pieces of bone, and obviously high-end industrial design, which is one of the more recent developments, is designers designing for three-dimensional printing and creating very interesting aesthetics. Here's the real-world application. Again, this was Renault Formula One at the time, and they needed 6 electronic enclosures for the car, very similar to some of the aerospace programs where you only need a very low volume. So this is not mass custom manufacturing. This is low volume manufacturing, where the cost of tooling, the lead time for tooling is excessive. So why bother? Just let the DVD be your injection molding tool. Put it into a computer, on-demand manufacture it, bolt it onto the car. Again, very light, complex nylon, tough nylon components. You see a lot of this under General Atomics, Boeing, Lockheed, all the different aerospace companies. High-end industrial design, I think we pretty much covered that. Again, this is, someone mentioned the International Space Station. We have over 1,200 components on the International Space Station are made from plastics made in our machines. In this case, it's a glass reinforced nylon and then a pure nylon 11. And I believe these may have been made by Rocketdyne in 98, 99. So just kind of close the loop there on that. Again, it was, the design was done on a Monday. The part manufacturing was done on a Friday. Certification was in the following week, and they were introduced or sent up within about a month from CAD file to physical part. Very, very lightweight, hollow internal structures, so high strength to weight ratio. Complex ducting, again, a really good application because a lot of complexity, very difficult to manufacture trapped space using conventional manufacturing. So again, moving air, electronic cooling ducts in this particular case for Formula One. Again, Formula One and jet fighters are exactly the same requirements. Very expensive, the demand for lightweight, lots of design iteration, very low volumes. So a great tool for manufacturing or making in that particular. We have full color printing. On the consumer end, Z printer, many of you probably already have this, but we're jetting ink onto cross sections. I don't know if anybody here is with the CIA or don't raise your hand, but there's an object in front of that gentleman's face, and it's effectively invisible. So one of the fun projects Scott and I are working on is building objects that you mount on a wall, like an octopus or a chameleon, and they're invisible because they're capturing the texture and the color of the object behind it. So, so for making little camera boxes and stuff, there could be some interesting applications. It's a project we did in Germany last week where we custom printed 200 people's faces at a trade show on the booth, scanning and printing and handing them USB keys with their faces real time. And it was interesting to actually do it and kind of be confronted by some of the challenges associated with managing the logistics once again. Color CAT scans, a bunch of companies are artificially assigning pigment based on density or blood richness. What you get is 3D models for diagnostics and for being able to study and understand exactly what's going on. For example, if there's a complicated bone tumor, being able to see it. And by artificially applying color, you just bring in that extra dimension of visualization. Just to close on the Cube printer again, I have an 8-year-old son, and I brought the Cube printer home, and I was training him how to use AutoCAD and how to use Rhino to create very simple geometries, and I couldn't get him to stick with it. After playing on a computer for 3 or 4 hours, he'd rotate. At the end of all that work and effort, he'd have a little 2-dimensional object on the screen that he would rotate, he would render it. But after a few weeks, he got bored of it. He went back to playing the video games and not really interested in the 3D CAD. As soon as I brought home a 3D printer and plugged it into the laptop, and 3 hours later he had a physical representation of his idea, it just clicked. And instantly he was completely back engaged. And giving somebody a reward or something tangible for that effort, that creative effort of interacting with a CAD package is very, very powerful. And that's kind of one of the reasons why we're doing the Cube and the consumer printers is, if we sell 10,000 printers and there's 10,000 people out there who now have an expectation that they can get a physical object within hours of having an idea. And that's intoxicating. You can't go back to the world of being expected to wait for a month for your prototype to come back once that timeline is elevated. Okay, so that pretty much concludes it. I have some parts if anyone wants to check them out.
So we're running a little bit over in terms of time, so I thought I'd bring the 3 up here. And if you have a question and we can't hear it, I will repeat the question and then they'll answer. That way we don't have to pass the microphone around.
I have a question for Rich. What metals are you able to create in your process?
Currently, the 2 structural materials we use, one's a nickel-cobalt alloy, kind of similar to stainless steel, probably hardened 304. But we also have a pure palladium for biocompatible and implantable applications.
Also for Rich, have you tried doing a microturbine yet?
Actually, we have made a microturbine, yeah, but we're running off of air, but it's really just a 1 millimeter turbine, fun little toy, but haven't found a really good use for it yet.
Way in the back.
Yeah, we have a few questions from people viewing online. The first is from a gentleman named Dick Herman. What areas of current manufacturing are likely to experience disruptive effects? And what is your prognosis for the SME manufacturer?
So what areas of manufacturing are most likely to have disruptive effects or suffer those effects? And I'll start with Autodesk.
It's hard to tell, because if you are adding additive manufacturing, I'm going to tell you a concept that I was expressed a few weeks ago. It was pretty much, you remember when we tried to bring the microwave into the kitchen many, many years ago, and we said that's going to replace everything in the kitchen. You're not going to need any cooking device or anything like that. And it's not true. It haven't happened. The same thing happened with the 3D printing. It's an element to facilitate different method of fabrication. I think other method of fabrication will still remain there, but one doesn't replace completely the other one. There are certain industries that additive manufacturing is right on. That's exactly aerospace, automobile, jigging, tooling, some of the elements are very, very key. My question to the manufacturer of the 3D printer is that we're still very limited in the amount of material we support, and that's kind of the things of the future that when we see an expansion of material that are certified, tested, then we will see a lot of more happening in the 3D printing.
So I guess that's a follow-on question for Patrick in terms of materials in 3D.
Yeah, just to answer the first question, I mean, we're seeing significant disruption in many industries. An example of one is prosthodontic dentistry, where the conventional workflow is to take an impression, FedEx it, 6 dollars, 24 hours, pour plaster Paris, then manually sculpt and carve to create a model onto which a crown is manufactured. That happens 70 million times in the United States every year, 140 million times outside the United States every year. With the development of very high precision three-dimensional printing and the advent of intraoral scanning, where a dentist can scan a patient's teeth directly in the mouth, it's now the dentist is able to scan the teeth, email the data directly to a dental lab, where they can fabricate a very high precision dental model very, very quickly with a significant reduction in labor. So when you talk about disruption, shipping, disruption to, because it doesn't cost anything to ship data, you can email data. Disruption to the plaster Paris industry, disruption to the impressioning materials companies. So that's, there's just one example, but there's a lot of that. The consequence of adopting digital workflows is there's some significant disruption. Okay?
From the position of bringing American manufacturing jobs back and increasing our effort here in California, you can see that 3D printing and additive manufacturing in general speaks well to California. We don't offer low-cost land, nor do we offer a low cost of living here. We offer a great lifestyle with a lot of very smart people, and this technology, I think, is going to be a game changer in a big way for California in particular, and for the United States as well. I think it will be disruptive, and I think it was a very good question. Next question. Yes, sir.
For the AutoCAD gentleman, I was particularly interested when AutoCAD sort of broke ranks and decided to give away 123 CAD. Is that the package to encourage young people to begin to design in 3D and so forth? I was always fascinated by how much controversy that created within the Autodesk organization.
Actually, not controversial at all. And actually, what we wanted to do is to unleash the imagination of people. People, hobbies, makers who wants to really didn't have the access of training of complex 3D design software. So we wanted to offer something that it was very easy to use and extremely affordable for them, and really try to unleash the imagination. The other thing that we're trying to do in that initiative, is not only on the design, as some of you guys mentioned, but, can I fabricate from there? Can I send it to the, either I have a MakerBot system that I can 3D print, or I wanted to send it, to a service bureau. We're offering all those tools. And just to give you a little bit of data right now, so in 30 years, it took us about 30 years to reach 50 million customers for AutoCAD. Took us 2 years for these consumer products to reach today 110 million. So it's really exploding, that initiative, and from us is to provide the best tools in design you can possibly imagine, to be easy to use, to be very affordable, and allow you to output something material.
More questions from the back.
One more from a viewer online, John Hines, specific to Microfabrica. Will the Microfabrica process allow for embedded microfluidic channels?
Will the Microfabrica process allow for microfluidic channels?
Yes, that's a really good question, and that is on the list of things that we could do. All additive manufacturing technologies can do. So even on our website, we show micro embedded channels, hidden channels. Another good example of something that's really impossible to machine.